Hello everyone and welcome to today's class. In the last class we talked about the definition of work. Now in thermodynamics work can be of different type depending on how the work is happening. Like work can be of electrical work, gravitational work or can be mechanical work. Mechanical work in other term is known as the pressure volume work. In chemical thermodynamics that we are studying in chemistry, we are going to deal with the pressure volume work, that is the mechanical work. Now, to define pressure volume work, we can take an example of an situation, a chemical transformation. Like, let's assume that this is a beaker. In this beaker, certain amount of gas is enclosed. This gas is enclosed with a piston. The piston is at a certain distance from the bottom of this beaker. Now, if certain amount of external pressure, let's say Fx, is applied to over this piston, which is having a cross section area A, in that case the pressure, external pressure that is being applied over the piston is going to be PEX. Px is going to be force applied or external force applied over the piston, cross section area of the piston, that is Fx by A. This is the pressure, external pressure that is being applied over the piston. Now if the pressure, external pressure is less than the pressure inside the gas, in that case the gas will expand. If the external pressure is more compared to the pressure inside this gas, the gas will get contracted. Let's assume that the pressure, the external pressure that we are talking about right now is lesser compared to the pressure of the gas inside this container that is enclosed. So if that happens, in that case we are assuming that Px is less than the pressure of the gas that is enclosed inside this beaker. So an expansion will occur, and as a result of this expansion the height of the piston will increase. The change in the height is going to be dx amount. A very infinite amount of height will be increased. Now due to this very small amount of increase in the height, in the distance, the work that will happen due to this pressure, due to applying this external pressure over this piston, it will going to be delta W. Now we know that by definition the expression of work is work equals to force multiplied distance. Now force is the Fx amount of force, Fex, and the work has done against this force. The change or displacement has occurred against this force. So a negative sign is going to be into the displacement. The displacement that had happened is the piston has increased, the height of the piston has increased dx amount. So external pressure Fx multiplied dx. Now we have calculated that Px equals to Fx by A. So we can substitute this Fx value with minus of Pex into A into dx. Now this A into dx is nothing but area into distance of an enclosure, which gives us the volume of that enclosure. dW equals to minus P external pressure into dx is the change in the distance, A is the cross section area of that enclosure. So what we are calculating in here is the cross section area of the enclosure multiplying the changes in the distance, that is the change in the volume, that is the dV. Now in the previous case the volume was V1 and after the expansion the volume had become V2 amount of volume. So if we integrate this value, we will get the total pressure due to this total work that we had done. The total work that we will get after this expansion process, PEX, integration sign V1 to V2 volume dV. So this is going to be our general expression for the work that we can get after doing some mechanical work or after doing some work, pressure volume work. We are going to study right now the pressure volume work in a reversible process. We are going to study this particular topic with the help of the last example that we had taken. In the last example, we had taken a beaker. We are going to again take a beaker and we will enclose a certain amount of gas inside this beaker. Now the gas is enclosed with the piston. The gas have a pressure of the gas P, capital P. The volume of the gas is V1. Now an external pressure Px is being applied over this piston. This external pressure, as it is a reversible process, by the definition of reversible process, this Px amount of external pressure is going to be infinitely small compared to the external pressure of the gas. I'm going to say it again. As we are talking about reversible reaction, by the definition of reversible reaction, the external pressure, and we are talking about expansion process, the external pressure is going to be less compared to the internal pressure of the gas. But as it is a reversible process, the external pressure is going to be infinitely small. The difference between the external pressure and the internal pressure of the gas is going to be infinitely small amount. So we can say that this external pressure PEX is equal to internal pressure of the gas minus of infinitely small amount of change in pressure. So Px can also be written as P, internal pressure of the gas, minus of dP, infinitely small amount of change in pressure. Now when this infinitely small amount of pressure is exerted over this piston, and Px, we know that expansion work is happening, is less compared to the internal pressure of the gas, expansion will occur, and as a result of this expansion the volume will change, volume will increase, volume of the gas will increase. Now this volume, increase in volume, is going to be equal to very small, very infinitely small amount, because the change in the pressure due to which this volume is increasing is infinitely small change in the pressure, that will produce an infinitely small change in the volume also. So the change in volume, which is in this case increase, is dV amount. So we are going to apply this in this, all these data that we have collected on the work expression. So by definition we can calculate the work that had done by the system as delta W equals to minus of P external into dV. This is the amount of the work that we will get by the mathematical expression of work that we had just studied. But this is an irreversible process, and we know that as it is a irreversible process, the external pressure can be written as P minus dP. So we are going to substitute the external pressure expression in this equation as delta W minus of P minus dP whole into dV, or delta W equals to minus P dV in plus dP into dV. Now this dP into dV product value is infinitely small amount of value, because both these changes, the change in this pressure and dP and change in the volume dV, is infinitely small quantity of change. So the product itself is a very small quantity compared to this minus P into dV value. So we can actually neglect this dP into dV value and write this expression as delta W equals to minus of P into dV. Now, this is the general expression for the work done by the system for a reversible process. In this process, this pressure term is the pressure of the gas, not the external pressure. This pressure term is the pressure of the gas, not the external pressure. Because as by the definition of reversible process, the gaseous pressure is almost equals to the external pressure. The external pressure is infinitely small compared to the pressure of the gas, and against that infinitely small amount of pressure, the gas is expanding in an infinitely small amount of volume change, with the infinitely small amount of volume change. Now this is the expression of the V work done. If the volume that was previously V1 changed to volume V2, in that case we can write by integrating the total work done by an reversible work done, W reversible, minus P, which is the pressure of the gas, into integration sign V1 to V2 into dV. We had just studied the general expression for the work done by a system when an isothermal expansion occurs. What is going to be the general mathematical expression of this work done by an ideal gas? If the gas that we had taken is an ideal gas, work done by an ideal gas in an isothermal reversible expansion. Now these words are very important. The first thing that we are going to that you need to remember, that we are talking about not any kind of gas. We are only going to concern our study right now for ideal gas, and these condition that we are applying, that we are doing an isothermal experiment, that is the temperature we are going to take constant, and expansion work we are doing, and it is a reversible work. Now for the reversible expansion, the work done by the system were given by total work done by the system for reversible expansion or reversible process was W minus of pressure of the gas into integration sign V2 V1 to V2 dV. This is the expression that we had just studied. Now let's apply the particular condition, that we are now going to apply this particular mathematical expression for ideal gas and isothermal condition. For an ideal gas, and at constant temperature, By applying ideal gas law, we can write P, pressure of the gas, equals to nRT by V. We can write that. So we can substitute this pressure of the gas expression in the main equation with this ideal gas equation, and can write W, total gas, is equals to minus of nRT into integration V2 to V1 to V2 dV by V. After doing the integration, we will get W, total gas, equals to minus nRT ln of V2 minus V1. By multiplying 2.303, we can transform this ln to log, as total work W equals to minus of 2.303 nRT log of V2 by V1. This is the integrated expression for the work done by an ideal gas in an isothermal in an isothermal reversible expansion. I'm again going to say that this is the integrated formula, integrated mathematical expression for the work done by an ideal gas in an isothermal reversible expansion. This can also be written as W equals to minus of 2.303 nRT log of P1 by P2, as from the ideal gas law or Boyle's law. V2 by V1 is equals to P2 by V2 by V1 is equals to P1 by P2. These are the two expressions that we can take help when we are dealing with an expansion process which is isothermal reversible and for an ideal gas. We just studied that work done by an ideal gas in an isothermal reversible expansion. Now, work done can also occur in an irreversible expansion. Let's study that. Let's first study how an work is done, pressure volume work is done in an irreversible expansion condition. Now, this is the beaker in which the gas is enclosed. This is the gas. It is enclosed with this piston. Now, Px, external amount of pressure, is being applied over this piston, and this Px amount of pressure is less compared to the pressure of the volume, pressure of the gas within this within enclosed within the beaker, which is P1. Now, obviously an expansion will occur. Now, as irreversible expansion occurs in a finite amount of change will happen. Let's see that dV, it is the volume change that has occurred, and this volume change is the increase in the volume because the expansion, the external pressure that is being applied is less compared to the considerable amount of lesser compared to the internal pressure P1. Now, after this volume change, this P1 pressure will change to P2 pressure. Final pressure of the gas. P2 is the final pressure of the gas and the expansion process is finished. Now, when this expansion process will finish, when the pressure of the gas, the internal pressure of the gas becomes equals to the external pressure, and automatically the expansion process will stop. So, the external pressure is actually equal to the final pressure of the gas in this process, P2. So, if we Now try to calculate the work done that had occurred. It is going to be the total work done, W is equals to minus of P external into dV amount. Now P external nothing but, sorry, P double R, W double R is nothing but is equal to the final pressure of the volume that will occur after the expansion process happened, that is minus of P2 volume into delta V amount of volume, because finite amount of volume has changed. So the expression becomes this one, W my W irreversible total pressure or total work done by the system for this irreversible process minus of P2 into whole into V2 minus V1. Now if this is the gas is ideal gas, if the gas behaves ideally, then you can write P2 equals to nRT, also isothermal condition I am applying to it, V2. Now let's substitute that value in here. We can add W irreversible equals to minus of nRT by V2 whole into V2 minus V1, or W irreversible equals to minus nRT 1 minus V1 by V2. This is the another form of the work done by the system expression for an irreversible isothermal irreversible expansion for an ideal gas.